So, in the recent years, space missions have been have been increasingly subject to security breaches, data breaches, and sometimes even satellite hacks. Most of the discussion revolve around space segment, so like direct means of communicating with the satellite. However, it is the ground segment that is going to be most likely targeted by the adversaries, and that's because it's large attack vector or attack surface. So in this presentation, I will give you a brief overview of the space and ground segment and how they relate to each other from the attack surface point of view. I will introduce you to SLE protocol and the security aspects of it, and then I will demonstrate a couple of exploitation techniques which potentially give you a possibility to take over control of a spacecraft. So every space mission can be loosely divided into space segment and the ground segment, obviously. Space segment is very complex. If you think about spacecraft, it's a very complex device. But then if you think about it further, it is just like one single point in a system. It has one interface, which means that from the attack surface, it is just one element, and therefore the attack surface is very small. And on top of that, the communication is challenging with the spacecraft, and it's not because of the technical aspects, but rather because of the environmental aspects, like visibility, orbit, or the distance between Earth and the spacecraft. The ground segment, on the other hand, consists of many interconnected components. They are all on the ground, and there are many entry points. Because of that, it creates or imposes large attack surface. On top of that, to hack into a ground station, you don't need any sophisticated equipment because it runs on a standard infrastructure. And also, most of the software that is developed for space industry is a custom development, which means that it creates or imposes potential avenues or additional avenues for new vulnerabilities. So at the extremely high level, this is how space mission more or less looks like. You have a space asset, which is on the space segment, and then everything else is on the ground, where you have a ground station, MCS, which stands for Mission Control System, and then you have some users which use MCS to communicate. They use MCS to communicate to the ground station and the spacecraft. So the point I'm trying to make is it's going to be much easier to hack into these things instead of build it if you actually want to try to hack spacecraft. So now about SLE. SLE stands for Space Link Extension Protocol. In principle, it's a protocol that lets the users to send commands to spacecraft and receive telemetry from spacecraft. It is based on the TCP, on the TCP IP. It supports encoding and authentication. And it can have two roles, SLE user and SLE provider. Now, SLE provider is a ground station, in a nutshell, and SLE user is a process which is going to run on the mission control system. So, in a nutshell, SLE defines a protocol for transferring PDUs using TCP IP for data transfer, and ASN1 for data encoding. In the system, if you remember the previous diagram, this is where the SLE is. It's a link between the mission control system and the ground station. And now if you are thinking or wondering who is actually using this protocol for space missions, the answer is absolutely everyone. So these are the most famous suspects. If you look at the documentation, you will find a list of agencies that take care of the development and maintenance of the protocol. And then, three times as many other organizations and entities who are actually using the protocol for the space missions. It is also present on most of the ground segment devices. There's this special equipment which runs in the ground segment. And also many organizations advertise it as a protocol on the list of their interfaces and capabilities, like in this case, the NASA Space Near Space Network. So for our research, we have decided to focus only on the commanding capabilities because we want to demonstrate how easy it is to take over a spacecraft if you have access to the ground station or the ground segment in general. So we focus on the FCLTU, which stands for Forward Communication Link Transmission Unit, and it's basically the thing that the users use to send commands to the spacecraft through the ground station. It defines a number of operations. The ones which we use in our exploitation techniques are the bind, unbind, start, stop, and transfer data. And you'll see in a moment what they are. From the security standpoint, because I mentioned I'm going to talk about security of the SLE, there is no data privacy. There is no encryption on the protocol level. There is a sequence numbering to potentially prevent operation injection, but that is trivial to bypass, which we'll see later. It comes with authentication, but again, there is no encryption. Only the credentials are encrypted, so it's very easy to bypass that using the man-in-the-middle attack as well. So in our testing environment, we decided to keep it simple. We have a SLE provider, which, as I mentioned before, is a ground station. In our case, it's just like a Debian machine with ESA SLE API implementation. We have SLE user, which is mission control system, with running on Debian, and another implementation of the SLE called Python SLE. It's a Python package. And this is just to demonstrate that it doesn't matter what implementation you use. As long as you use SLE, you're going to be vulnerable because the implementation follows the standard. Otherwise, it's not going to work at all. And of course, we have an attacker machine somewhere in the middle. So this is an assumed breach testing scenario. So the adversaries are already in the network. As I mentioned before, there is no encryption. So we thought that the best way to demonstrate this, or the most impactful way to demonstrate this, is going to be using the man-in-the-middle attack. So we basically start with the ARP spoofing. We capture the TCP frames. We decode the TCP frames, or the data that they carry in the data field, which are the ISP frames, and I'll tell you what it is in a second. We manipulate the CLTUs, which are the elements that will go to the spacecraft, and we update the TCP frame and then forward to the destination. So like in any other man-in-the-middle attack, we poison the ARP tables between the mission control system and the ground segment. We make the traffic go through the attacker's node. We capture the TCP frames, put them in the NFQ filter for the in the NF filter queue for the processing, and this is actually where the fun begins. As mentioned before, we are operating on the TCP level, or at the TCP level. So the TCP frames data field contains the PDUs, the data units in the ISP1 format. Now, ISP1, it is an extension of ASN1 encoding or format, which means that to decode it, we simply use TLV values, TLV fields to understand what are the values. There are custom and context-specific structures and sequences, but they are specified in the documentation, so it's very easy to find what they are. And so once we understand what those structures are, then we can do the mapping to the FCLTU data type specification, which is also in the documentation. So this is how it looks like. This is an example of a CLTU bind message that goes from mission control system to the ground station. You can see that there is header, there is like typical structure of the TLV, and also somewhere there you will find credentials. So I will start with some demonstration now. I have a couple of videos recorded, But before I show you the exploitation techniques, I will show you how the nominal behavior works or looks like, how the nominal communication between the mission control system and the ground station looks like. So in this video, you will see a CLTU bind message, which is basically going to be this byte of string byte. We're going to send the start, which will set up some ground station equipment at the ground station, and then we're going to transfer some data, then we're going to do stop, and then unbind. So that's how the nominal communication would look like. On the top you have the SLE user, which is mission control system, and then SLE provider on the bottom, which is the ground station. And of course, it doesn't play. Okay, I'm prepared for that. I'm going to try to play this way. So you're going to see this sequence of actions throughout the rest of the presentation on other demos. So as I said before, we start the ground station at the bottom, and then we run our routine on the top. The mission control system is communicating and sending some data to the ground station, which in the end will be sent to spacecraft, because ground station is just a thing that pushes forward the telecommanded products. So that's how it looks like nominally. Now there are a couple of things we can do about it to make life more difficult for the operators. One of them is to prevent authentication. The reason why it's extremely annoying for the users is because there is no, at the protocol level, there is no feedback when you fail authentication, which means that if you fail authentication, the ground station is gonna drop down the connection with no indication whatsoever. You have no idea, as a user, you have no idea what's going on. So it's gonna be quite interesting to see that actually in practice. So what we do here, we capture the frames with the bind message. We mangle the credentials, and then we push it forward to the ground station. So the setup is pretty much the same, except that on the left-hand side you have raw exploit that runs the man-in-the-middle attack. So we start the ground station, and we go about with our routine. We connect, we bind. Oh. Okay. That's because I'm still in the presentation. I swear it worked when I was testing it. So, ground station, mission control system, we start our routine. We send the bind request. We capture credentials, by the way. And we are in a weird state that we cannot... hold on. Okay, this was just about capturing the credentials. It was not mangling. Okay, let me reverse it back. So what you have just seen, it was a demo that you can actually capture the credentials. You can store it for later use, and then you can use it to establish your own SLE session between attacker's machine and the ground segment and the ground station in order to hijack the communication of a spacecraft as if you were the legitimate user. So that's how you were capturing the credentials. Now let me show you the next one. Of course, it is very tempting to start mangling with the data that you actually send to spacecraft. It's a nightmare now. So what you will see is, again, standard communication between the mission control system and the ground station. But instead of messing up with the operations, we're going to actually capture the data. We are going to be looking for a specific byte string, and then we're going to change it to something of our liking. So as you can see on the top, we have our exploit. We are searching or monitoring on the wire for a string of bytes. And then once we see it, we're going to change it to something else. And this is what's going to be sent to spacecraft instead of the actual telecommanded products. So we start our exploit. Start on ground station. And again, the users go about the routine as per usual. Now you can see that the users have sent a byte string from 0 to 9 hex. We have captured it, and then we send it something else, what we have defined in the exploit. You can see that there is no integration check. Neither MCS users nor ground station have realized that you can actually do that, or someone has actually done that. So we are still operating in a stealth mode. Okay, and the last demo I have for you is when you try to take over the actual SLE session. So what you will see is we're gonna put all of that together. We're gonna capture the credentials. We're gonna modify it in order to fail the user authentication process. But we're gonna establish our own SLE session using the user's credentials. And from that moment, we will be able to command spacecraft or try to send the commands which will be delivered to the spacecraft. Setup is pretty much the same. On the left-hand side, at the bottom, there is our attacker's mission control system that's gonna be pretending to be the legitimate one. And we run it. We do exactly the same thing as before. We capture credentials, we fail the authentication. Only ground station knows that authentication failed. The user has no idea, but we capture the credentials and we establish our own SLE session as if we were the legitimate user of the ground station. So from now on, we can command a spacecraft to our liking. Okay, conclusion. What you just have seen is just one way you can actually think of taking over control of a spacecraft if you know what are the vulnerabilities of the SLE protocol. In our research, we only focus on the telecommanding capabilities because we wanted to render as much impact as possible, but of course you can also start your operations in a more stealth mode and process the telemetry and also modify the telemetry so then the operators don't know what is happening because it's going to be false. If you want to have a meaningful communication with a spacecraft, there is some spacecraft knowledge required because you need to understand the commanding products which you are sending to spacecraft, or the spacecraft has to understand what you are sending to it. But otherwise, all the knowledge which I have presented, it was gathered using the OSINT. So all the documentation is made available publicly. And so anyone can do the research. CCSDS, the standardization body which is responsible for SLE, they came up with Space Data Link Security, which is basically imposing the encryption on it. However, they have done that only on the link between the ground station and the spacecraft itself, which means that the link between the mission control system and the ground station is still vulnerable. And we are now working with them to enable TSL-like features on the ISP1 level in order to mitigate those issues. So for the further work, we are planning to run some tests on the actual ground station, which we know that ESA's MyLab, they have Cortex devices, so our idea would be to actually demonstrate it on the actual ground station devices. And then we're going to further work on the exploit with coming up some additional ways to demonstrate these vulnerabilities of the standard. And I guess at some point we're going to open source it. So this is a list of references. You will find the whole list in the publication. As I said, everything is open source, so you can do your own research on this. And our research you can find on this URL. We have done some additional research on other ground segment and space segment applications, mainly from NASA open source software. So if you are interested in that, you can just follow the links. I guess I can give it later after the talk. And that was the last slide. Thank you very much.
Yeah, thank you, Andy. Any questions from the audience? There's one question over there. Let's see. Wait for the microphone. That way NASA can also listen in to what you're asking.
Thanks a lot for your talk. Do you have any insights on real-world attacks leveraging the methodologies you described?
No.
Okay, thanks nevertheless.
And any other question? Bianna.
I have a question on the slide at the beginning about confidentiality and integrity protection. You were saying there's a sequence number, so that helps you with replay protection. But what is actually there for integrity protection of a message?
What is there to do what?
So you had this slide that talked about confidentiality and integrity protection, right? You talked about a sequence number. So a sequence number helps with replay protection, but it does not provide integrity protection. So my question is, what is there for integrity protection of a message?
There is no integrity protection. You can put whatever you want.
Okay, so you sequence.
So that's the whole point. That's the whole point. Yeah.
Right. So the sequence number is also useless.
Yes, absolutely.
Okay, thanks.
That's what I say. It's trivial to bypass.
Any other question from the audience? No? Going once? Going twice? Well, thank you very much, Andy, again, for the great talk. It was really far out there.